Hello, everyone. My name is Petr. I'm co-founder of OXORIO. So we do security audits. Our focus is solidity, and now we also start to work closely with different ZK solutions. We did several ZK audits, and I want to show you some traits that what you need to know when you do security audit as developer or security researcher, and what the difference with the traditional like solidity tests that you need to do. Can I use this? Yeah. Okay. So first, I will briefly explain like what is ZK and how it works. Then what the kind of attack vectors we have and how to mitigate them. The basic, what is circuit, and I think first what is like zero knowledge proofs is complex layers of the things. So you have proving system, algorithmization algorithm, and then you have a circuit. So I will touch maybe only the circuit part, that like the code that you write, but you always have to remember that you work with a complex system with a lot of elliptic curves, cryptography, hashing functions, and mathematical under the hood. And all these layers are affect the last layer. I will tell about this later. But when you're talking about circuits, it's more about like functional programming. And it's the circuit in Circom looks more like traditional hardware circuits. Like is a pointer? No, there is no pointer. Okay, and the basic things, you work with these signals, and you operate with like series of bytes with traditional operators if you're familiar with circuits like OR and XOR and others. So there is no complex mathematical things that you can do, and you always need to think like this is like series of signals that you work with. Okay, the very basic and first most common thing, it's like in Solidity you have reinforcer that you can find in every second smart contract. And here in Circom, you always will see under constraint circuits and non-deterministic circuits. So in general, it's similar things. The difference if you have to check the inputs and outputs. For example, if you doesn't check outputs, you can get your soundness, the basic things of ZK will be broken. So your proof doesn't guarantee anything at all. So there's a problem if you not work correctly with outputs. If you didn't check for the inputs, it means that prover can generate the proof of something that's valid, but you get it in the input invalid parameters. So it also is very easy to make a critical bugs, because then there is no make sense. You can put some invalid data and make a valid proof. And this is a very how it looks in Circom. So you have operator, assignment, and constraints. Very easy to mess with up. If you have like minus minus, it's assignment. It doesn't check anything. It's just assign signal from one point to another. And constraints check that that something that you have from the right side is correct. And the most of the bugs will be related to these things, because it's very easy to forget and mess with them. So let's go to the example code. So let's imagine you want to multiply, you want to prove that you know the two numbers, and that multiplying by them, you get some public big number. So this is a basic circuit, and we have like so here is a check how it looks. You have signal factor 1, factor 2. This is your inputs, secret inputs, and signal signal val is public input that you check, that you know that by multiplying these two factors you get this. The issue is that you can just simply check like in one line. You need to I highlight the problems. So you need to check that the numbers are not equal to 1, because otherwise you can just simply put 1 into the first signal and same to val into the second signal, and you easily can pass these checks. Also, there is a you work with the elliptic curves, that you need to know that there is a prime number, and you need to work with there is no negative numbers. Just rule of thumb that we use the second half of the numbers as a negative numbers, but there is no any libraries that check it. You need to remember it. Also, developers have to put it into the documentation, so everyone know how to work with your signals. And also, you always need to check that all these numbers not exceed the order of the finite field. So now go to the hardest thing, how to fix it. The one line goes into all these things, just to check that you know the two multiplication by two numbers. So first, we need to check that our numbers, the num2 bits is a general function from framework. It just converts your signal into the array of bits. So usually you have to work with the bits later in your code. That's how it works. So you just check that, so their numbers are positive, so you know after which bit you have the negative numbers, and you just check so they're in your range. This is a bit different. It's like new balance. There is another difference, but exactly the same checks that you need to do. This is a checks for they are positive. This is a check that they are not exceed your finite prime field number. And also, like, just to simply check that your value is not equal to 1, you need to use the special function is0, do all this operation with the signal just to simply check that it's not 0. So you see, it's not that easy as is just solidity. And if you want to check that is equal to 1, you just deduct from your signal 1 and check that if it's 0. So it requires a lot of additional checks, and it's very easy to overlook. Okay, so overflows and underflows, I already explained what is it, so I will just skip it. So we already talked about this. So same as in traditional like programming, you can overflow, and there is can cause a wraparound effect, but you need to know that you work with elliptic curves. There is the different elliptic curves has different prime field number. It depends, may vary, and you always need to check they are not exceed. Otherwise, you can just do double spend. That's what happens, could happen with Tornado Cache. But they fix it, but they used BN254 elliptic curve, but in Solidity we have 256 bits. So it allows you to just send the higher number than and do overflow and do double spend from Tornado Cache. Luckily, this is an example like exactly how it was in semaphore. Doesn't matter. I think it's everyone knows what is overflow. So you just exceed the prime number, and that's it. So that's the example of vulnerability you can find and see that there was a very interesting thing happens in like GitHub. So Roman Semyonov, one of developer who work on ZK, found this vulnerability that allowed double spend. It was affected by so many libraries. It was in 2019, and it affected all the libraries that we used at that time. So it's Miximus, Socrates, Snark.js, all of them has the same issue. So that's very basic things, but this just highlight us that ZK development is only early stage, and all the frameworks, we need to just double check them, how we did them well, do formal application, fuzzing, whatever you want, but just please keep an eye, because I am pretty sure that there are still some issues that we will find later. Another thing is about bits. You always have to remember that you work with the bits, and if you will see that there is a correct number, if there is a bit length will be different, there also gives you possibilities to manipulate with your signals. This is an example, like you can just add extra bit and pretend that you have a 9 instead of 1. I will show you. Yeah, so I will not go into details for now. I can share presentation. You can just check explanation, everything. Now I will just show how it can easily could be mitigated. So you always need to use like less than template and check that max bits not exceed that you expect there. And you need to check everything, right? Like input 1, input 2, and after calculations, check the output that it doesn't exceed last bits. One more interesting thing is problem with the compiler. There is no special flags like to ask compiler to not optimize your inputs. So if you don't use some kind of inputs, compiler just move it out, and sometimes you need to add to your proof some additional info to use it on chain. For example, how Tornado Cash use it, they put into the public input information about relayer. So when you generate proof, you put it on chain, and there is some information who is relayer, how they and all additional info that you don't use in the circuit directly. You can easily lose these things if you don't know about this issue, and then everyone can generate as many proofs as they want with different inputs. So this is a sound that is broken. How easily to mitigate these things? You just add some artificial calculations in your code. Then, for example, you have a signal, you just multiply it by itself, add constraints, and voila. So you can work with this. Of course, it's better to fix it by some compilers flags, but it takes time. So we have to work with this in this way for now. One more rule of thumb: don't use sound cryptography. We saw it so many times. People try to optimize the cryptography. They don't read documentation, and it causes a lot of issues with their code. So it's very important to read all the documentation, even for simple functions and hashing algorithms that you probably know how to work with them, but actually it isn't. You can find a lot of interesting things in zkdocs.com. Is the code is a site from Trail of Bits, and they have a lot of explanations how to use different kind of things. So, for example, this example like how to work with the Schnorr protocol, like Fiat-Shamir secret sharing, and everything else. They have bad example, recommendations, and this is like hidden gem for developers who want to become a cryptographer. Yeah, and don't use now you can see there a lot of new proving system appears in the market. Some of them add recursion into the snarks, the folding schemes, pairings, and so many things happens. It's very hard to check all of them. For example, like security standard is Groth 16, that all the most of the projects use it in production. There is also Halo and Plonk appear in the prod, but you will find so many new things that probably gives you a lot of advantages, but they are not tested yet in production, and most of them are just like like research paper without any security audits. So check it out. And this is an example again about frozen hard vulnerability that found in Plonk by Trail of Bits. So everyone was a lot of expectations to the Plonk, but later Jim Miller found it, and he has a very good presentation. It was on DEF CON from Japan. You can find very interesting to see how they found it and all the information about this there. Okay, another thing that you need to check, if you can, of course, it's trusted setup mechanism. That's something that you, who know what is a trusted setup? Raise your hands. Okay, half of you. Okay, so trusted setup is a special algorithm that you do before you can use snarks. I don't know how to explain easily either. This is a multi-party computation that a series of people have to do, and they compute some algorithms, then they send result of their computation to next person, and they have to delete everything that names toxic waste from the computations they did. And as many parties involved into this trusted setup, as more secure your snark will be. So the only thing when it will be vulnerable, and if all of the parties who involved in trusted setup will combine all their toxic waste, and then they can generate the fake proofs. That's how it should work theoretically. In practice, we have trusted setup leak in Zcash. It happens in 2019, because some of the data that before they assumed that it's not related to the trust setup, and like some defined as not toxic waste, appears it's linked to the key parameters that they use to generate all these things. Simply words, it means that some malicious actor can, if they use this vulnerability, they can generate fake proofs in Zcash implementation from 2019. Luckily, they fix it quite fast and make security disclosure, explain what happens, and we hope that nobody affected by this. So, but it happens, and it's very hard to check if you are not cryptographer, but it's better to always keep in mind that this. Okay, so now most recent part is I want to share some example of our latest audits of privacy pools. It's a new, it's Tornado Cash that they get rid of all the issues that Tornado Cash has with the legal part, because you can generate the proof that you are not in the set of some bad guys, and you can easily separate yourself and say, hey, here is my private money, and it's not that money laundered money. So that's very interesting thing. We work a lot with they have very good team, they do a lot of research, but still we found a lot of critical bugs. We already fixed them, but you can find, I want to just show example of how you can break all these things at once. So this is a num2 bits manipulation. What happens there? So they first they start to write their own cryptography, which is totally wrong. So they try to fork num2 bits that I showed you before and add some logic on top of this. So better to don't do this, even if it's not super optimized. It's better to don't change something that works correctly. Second, they use assignment instead of constraint. So it's very easy to check. Actually, do you want? Yeah. Okay, we have one of our auditors here who just work with this closely, so I will let him explain you from the first month.
Yeah, thanks. So while we have been auditing the project. There was problem with isNum2bits template. Basically, main functionality of this template was about constraint some signal that this signal is less than exact following of bits. For example, 250. For example, so they tried to fork template is num2bits and add some custom logic. Basically, this part is responsible to get first signal and convert it to the array of bits. And we have some parameter like n, which is the number of bits which must be in this template used. For example, like 284, as I remember, was defined in the protocol. So then what there happens that we go to the loop, and in the loop we take each bit with shift right operation and end with 1 what is assigned to the array of out for each step. There is a problem with assignment because it's without constraint. It is because AND operation, when we have some bitwise operation in the right side, we can't do constraint with assignment. So basically, they used this simple arrow, which is basically only assign value to the out E. Then they check that this assigned value is binary. Yeah, it's basically checks that with already constrained. But at the end of the day, we have problem that there is just check that one value is equal to another. And seems like everything is good. And at the end, we assign with constraint to is lower signal out of is equal. Seems like everything is good. But problem is that there we have constraint only that value is binary, that only 1 or 0. But attacker can manipulate this value, generate fake, not a fake signals, but insert incorrect values which will follow constraints, but basically break the logic. And this, okay, there is a snippet of the code that there was value 240, and then this value is used to determine what kind of action do in the project. So it's deposit if value is less than 240, and if it's greater, then it's withdrawal. And if we can manipulate such a value, which is we get from isNum2bits, then we can manipulate type of operation, and it's lead to very big problem in the following part, and many and big sum can be affected from the protocol. So basically, it's one of the issue which we found, and you can get familiar with full report in our GitHub repository with public reports. So there it is.
Yeah, thank you. So basically, you need all separate all the things. Don't combine all that at once. So they put checks, constraint, and copy of the template. And if they did it separately, of course, your snark proof will be much more longer and complex, but it will be secure. But it's very hard to find it, you know, like it's things that you always need to just check. So what I can recommend to developers like to mitigate this issue, so I combined the best security libraries that we have now to like static analyzers by stable bits. There is some fuzzing tests in some of them, fuzzing framework, and like just check these things. You will find a lot of things like to write the test, to fuzz, and do like some basic static analyzers. We also work on the writing. Want to make our more advanced static analyzer, but it's not that easy when you work with low-level things. Okay, so in general, like I want to just highlight that ZK snark programming is completely different. Just pay attention because it takes like many months to learn the cryptography things, and we spend a lot of time on this, and we bring a lot of cryptographers to our team to like migrate from just traditional Solidity to ZK. And also it will be very good if you know how functional programming works. It will give you like extra points. Check the common bugs and pitfalls that I highlight you, like, and others, like, but most common is under-constrained circuits, arithmetic overflows, and the most known like frozen heart and trusted setup leak. You can easily Google it and you will see it. And please check the community chats. There is like a lot of ZK chats, because I see that every month you'll see something new happens there. So new tooling, some new proving system, and if you want to be on the cutting edge of this technology, so you always need to check in the forums and chats, because it's very fast development things. Okay, if you need any help with your ZK things, consultation, or just want to know how it works, I'm happy to chat with you here or later online. And any questions here or later, welcome. Thank you. Well, I don't check what they changed from the versions. I just know like the latest major update of Circom, when they start to use assembly inside, and they just improve a lot of proof generation, speed of proof generation of the proof, like increased like 10 times or hundreds. Of course, they now we use 2.0.0, and they as far as I remember, there was no like critical issues in the previous one. They just add more useful functions that help you to write it more easily. Yeah. So, but yeah, we always check what happens there. Yep. Okay.
All right. Thank you.
Thank you.
So much.